Today I'll talk about ARIMA Time Series Model. It is my second lecture on sales forecasting, which is a part of series of my lectures on operations management. Today I'll cover the theoretical aspects of ARIMA modeling and the practical aspects with Python codes I will cover in my next lecture. So a stochastic process is defined as a random phenomena which is a function of one-dimensional parameter, namely time. So this is a stochastic process. This one is discrete and this one is continuous. A process x sub t is stationary time series if, so this is a definition of stationary time series, if its expectation is zero or constant and its variation is constant and there is no seasonality. So these three conditions must be met to call a series a stationary time series. A model in which future values are forecasted purely on the basis of past values of time series is called autoregressive process or AR process. So this is an autoregressive process when the future value depend on previous values, and these are the parameters which we need to estimate, and this is a white noise with the mean zero and a particular variance. So if this is a set of white noise, then this future value, if it is dependent on noise with these parameters, then it is called moving average process or MA process. Hence, the complete model, that is the data, is equal to pi as a function of previous values plus white noise plus theta as a function of previous values is known as ARMA process. If we need to make time series stationary, then process is called ARIMA, where I is present in the center, and this means integrated, autoregressive integrated moving average model. So how to make time series stationary if it is not stationary? Non-stationary time series with respect to mean may be either with deterministic trend or with stochastic trend, and the deterministic trend model is given by this representation where the future value depend on the time, and the stochastic trend is given by this model where the future values depend on previous values. And to make these series stationary, we need to do differencing. So now let us say what is the logic behind differencing. For deterministic trend, if this is the representation of deterministic trend model, if we difference the two values, adjacent values, that is z sub t is equal to y sub t minus y sub t minus 1, then it becomes, because this will cancel out and it becomes this. So the expectation of this representation is constant because expectation of these error terms is zero. So we are left with this term. So it is constant, and variance of z sub t is the variance of these error terms. So this is also constant. So this is how differencing make time series constant if it is a deterministic trend. If it is a stochastic trend, similarly, we can do differencing and this becomes stationary. This is a proof of it. The assumption is that the difference in adjacent values is more or less constant. So now I will consider in detail the simple AR model or AR1 model, and we will derive some useful information from the simple model. So if this is a simple model without a constant term, and this is a stochastic trend model. So if we substitute the previous value in terms of more previous values and we keep on doing it, then our series become the series of error terms. Hence, the AR1 model is same as MA infinity model. This is very important, that AR1 model is same as MA infinity model. The other thing is that this MA infinity model, the expectation is expectation of this term, because expectation of error term is 0, and variance of this series is given by this. And now we have three scenarios: whether the value of parameter is less than 1, or value of parameter is more than 1, or value of parameter is equal to 1. So these are three situations, and we will consider each one by one. So first, let us say the value of parameter is less than 1. So if value of parameter is less than 1, then expectation of this time series is expectation of this term. And since this term uh, is constant, so the expectation is constant. And variance of this series is equal to this. And if we substitute this parameter as equal to 1, then we get a constant variance. So if the parameter is less than 1, the time series is stationary. So what if parameter is equal to 1? This is very interesting scenario. If this is our time series, so if we put our parameter as equal to 1, then expectation of this series becomes expectation of y is 0, and that is constant. But the variance becomes this term, and this term is dependent on time, so this is not constant. So variance is not constant, expectation is constant, and this is known as random walk model. An example, very interesting, Brownian phenomena is example, Brownian movement and stock market prices. They usually are an example of random walk model with the parameter equal to 1. And these random walk models are most difficult to forecast. So how to identify that our parameter is equal to 1, or this is also known as unit root. So we can use augmented Dickey-Fuller test, where the null hypothesis is that our parameter is equal to 1, that is the time series have unit root. And the alternate hypothesis is that the parameter is less than 1, which means either stationary or trans-stationary model. Now, how can we make this unit root model stationary? As we have seen before, we can do differencing. And if we do the differencing of a model with unit root, we get expectation as 0 and variance as variance of the error terms. Now the third scenario is that the parameter is more than 1. So this is our model. So if we put as parameter more than 1, then expectation becomes infinity, because a value of more than 1 raised to the power t will of course become infinity, and the variance of the series is given by this term, which keep on increasing, so the model is not stationary. So if parameter is more than 1, the model is not stationary. Now we look at how to derive our ARIMA model. And to identify the parameters of ARIMA model, we need to look at the ACF and PACF graph. ACF means autocorrelation function, and PACF means partial autocorrelation function. So we can calculate the correlation for time series observation with observations with previous time step. That is correlation between present value and some previous value. This is called a serial correlation or autocorrelation. An autocorrelation function is used to determine whether an autoregressive model is appropriate. And interestingly, for a stationary time series, the autocorrelation declined to non-significant levels quickly. However, when trends are present in time series, Shorter lag typically have large positive correlations because observations closer in time tend to have similar values. The correlation taper off slowly as the lag increases. So this is important that it taper off slowly. And when seasonal pattern is present, the autocorrelation are larger for lags at multiples of the seasonal frequency than for other lags. And this I'll illustrate you with the help of ACF graphs a little later now. Now, partial autocorrelation function. A partial autocorrelation is a summary of relationship between an observation in a time series with observation at prior time step with the relationship of intervening observations removed. So it is the correlation between values at two timestamps or two time steps, removing the correlation of the values in between. The PACF graph is used to choose the autoregressive integrated moving average model terms. This we will see now. So how to make ACF and PACF graphs with Python? This is the code. Uh, I'll take another lecture with much more detail on Python codes, how to analyze the time series. So now let us see some of the graph. This is ACF graph when there is trend. So this is our time series with a trend, and this is ACF graph. The autocorrelations, they gradually taper off. This is our time series with seasonal pattern, and this is ACF graph. So it has a periodic correlation spikes. This is a golden table for ARIMA identification. This I have taken from this very informative YouTube video. So if ACF graph display a damped exponential and or sine function, then we can make use of AR model by looking at PACF graph. If PACF graph demonstrate a dominated damped exponential or a sine function, then we can use moving average model with parameter from ACF graph. This is very important. So if we look at this graph, the ACF graph shows a damped exponentially decreasing autocorrelations. So we can make use of AR model, and the parameter is, because this is single correlation which is important in PACF graph, the parameter is 1. So this is the AR1 model. In this, there are two correlations which are important in PACF graph. So this is AR2 model. In this, there is damped exponential tapering of PACF graph. So we can make a moving average model. And since this is single correlation, which is important, so the parameter is 1. So this is moving average 1 model. Here, both the graphs, they show exponentially damped correlations. So we can make use of ARMA 1-1 model. These graphs, they show a periodic pattern. So there is a seasonal component. And this is showing a damped exponentially decreasing correlations in ACF graph. And we have a single significant correlation in PACF graph. So we make use of AR model AR1 with MA term as 0. And what about seasonal component? The seasonal component, these periodic components here in PACF graph, they are more significant as compared to ACF. So here the seasonal component is with AR term of 0 and MA term of 1. And the periodicity is of 12 months. So this is seasons 12. So this is the seasonal model. Now these are interesting rules which I have taken from this resource. Anyone who is interested in these can pause the video and read these. These are very interesting rules, most of which I have already covered. So this is all for today. Thank you very much.